So all exam grades are up now, finally. And hi. Homework 4, I just posted a moment ago. It's a pretty short one. And I'd like to shoot for having it turned in by Sunday, this upcoming Sunday. If that's not reasonable and you need more time, let me know. But that's my goal. So let me introduce you to the new assignment. It's a predictive modeling problem. So this statistical learning stuff. And I want you to use the baseball data we've played with and use 2 classification techniques. The supervised learning problem is of 2 different flavors. One is if your response is numeric, and one is if your response is categorical. And with the categorical response case, we do what's called classification. So in this case, in the Hall of Fame data, your response variable is yes or no, is a player in the Hall of Fame. And you're going to use the same predictor variables that we've played with in class. Hits, home runs, RBIs, and so on. These 6 predictor variables. And I've mentioned in class that there's lots of different ways to build a predictive model. Fundamentally, we're trying to say that a response is some function f of some predictor variables. So how do we define f? One simple way to define f with categorical variables is called linear discriminant analysis. And one slightly less simple way is called quadratic discriminant analysis, LDA and QDA. These are the ones I want you to use. Both of these are approximations of what's called the Bayes classifier. So I'll say something about this in class today. But for the classification problem, if the goal is to predict the value of a categorical response, and there's lots of different ways to do that, how do you choose which way and which model to use? So you would prefer a predictive model that is accurate. If you have 5 model choices, you would pick the one, all other things being equal, that gives you the highest accuracy. It turns out that if you specify a probability distribution, a likelihood for the data that you observe, then the best classifier you can do in terms of minimizing error rates is called the Bayes classifier. I'll show you again in lectures soon. But basically, the Bayes classifier is the classifier that assigns prediction to the group or the class that has the biggest probability, posterior probability specifically. So let me write something down just briefly here. Our training data, remember, looks like this. The predictor variables are in the X matrix and the response is in Y. So if we can say the probability distribution of X conditional on Y. If we can postulate what that might be, suppose x is just a single number. It's not p numbers, it's just 1. And y is, are you obese or not? Maybe x is BMI, y is obesity status. Then we might say that we think for obese people, the distribution of BMI is such and such, normal, centered at a particular place with a particular standard deviation. And for those who are not obese, we think the distribution is normal again, but with a different mean, possibly even a different variance. So if we're willing to postulate a particular distribution of the response, or of the predictor given the response, and if we're willing to postulate what we'll call a prior distribution on class membership, the F is a likelihood, and the G is a prior probability. So likelihood is a probability statement, like a joint probability is basically what it is, of observing your data considered as a function of the unknown parameter. If we're predicting class variable, then our parameter is y. It's the unknown class. Obese or not, spam or not, cancer or not. So the likelihood is like a probability of seeing the predictor variables that we saw. The prior is independent of the data and the predictor variables we saw. What do we think is the overall probability for an arbitrary person that they are obese? So we're imagining going out to the whole population that we're considering and randomly selecting an individual prior to seeing any of their covariates, whether they're male, female, or what race they are, or any of that. Regardless of all of that, my prior belief, my prior probability that they are obese is such and such. If you can state these two quantities, then you can apply Bayes' theorem, which says a very relevant thing for classification. Bayes' theorem allows us to combine a likelihood and a prior into what's called a posterior. So let me just call it H. The posterior distribution is a distribution for the class variable conditional on the observed data. And Bayes' theorem allows us to say this is proportional to the likelihood times the prior. Stat 101 Bayes' theorem is a conditional probability result. What's useful about it or unique about it is that it allows you to switch the ordering of conditional probabilities. Whereas the likelihood is a probability of the data given class. By applying Bayes' theorem, we get back the probability distribution of class given data. For classification, that's a very relevant quantity. What's the probability you're obese given your covariates? So, in the homework, I reference Bayes' theorem, and I reference what's called the Bayes Classifier. So the Bayes Classifier says predict the value, y hat, that corresponds to the highest posterior probability. You postulate a likelihood, you come up with a prior, you apply Bayes' theorem to get posterior probabilities, and then your prediction for a given individual with given covariates is based on which of the classes has the highest posterior probability. Given the data, the probability this individual is obese is 0.6. The probability they're not obese is 0.4. So my classification will be obese because the highest posterior probability is that they are obese. That's Bayes classifier. It's a pretty general technique. For an arbitrary likelihood in prior, you just apply Bayes' theorem and classify to the class that has the highest posterior probability. So the useful result is that as a strategy for classification has some optimal properties. In particular, it has the lowest misclassification rate of all comparable classifiers. What that means is, if you want a good classifier, you'll do well to try to mimic the Bayes classifier. And that's what LDA and QDA do. Both LDA and QDA postulate a normal distribution for the likelihood, and then we have to decide ourselves what to do about priors. But the big piece of LDA QDA is that this likelihood function is a multivariate normal. So I want you to apply LDA and QDA. And in a two-class problem, by that I just mean there's only two possible class values. You're either, in this case, in the Hall of Fame or you're not. If what we're going to do is compute posterior probabilities, we're going to have two posterior probabilities. For any individual, there will be a posterior probability they're in the Hall of Fame, and a different one minus that one, that they're not in the Hall of Fame. So the Bayes classifier, when there's just two classes, will just be classified to the class that has a posterior probability greater than 0.5. If there's only two, one of them has to be bigger than 0.5, unless there's a tie, in which case flip a coin or something. But classify to the class that has the highest posterior probability. And with two classes, that means greater than 0.5. In R, when you go use the LDA and QDA functions, that's what it's going to do by default. But we don't have to use 0.5 necessarily as our threshold. In the Hall of Fame data, there is a relatively small proportion of players who are in the Hall of Fame. It's pretty rare. So you're not, if you do these techniques, you're not going to get posterior probabilities greater than 0.5 very much, if at all. Which means your error rates are going to not be great. So the point of this problem is to give you practice in a common task with classification or predictive modeling, and that is tuning a predictive model. LDA and QDA are both predictive models. Pretty much any predictive model, there is at least one parameter for it that you have flexibility with. In our case, in this case, a parameter we have flexibility with and might consider changing is this probability threshold. I'm going to predict a player is in the Hall of Fame if their posterior probability is bigger than something. Call it kappa. We could define our classifier as I'll predict you're in the Hall of Fame if my model-based posterior probability you're in the Hall of Fame is bigger than 0.1. Or we could make it even bigger than 0.5. We could say I'm only going to predict you're in the Hall of Fame if this probability is bigger than 0.9. Whatever you choose, whatever that threshold is, you're going to have a corresponding set of accuracies. And so what I want you to do in this problem is consider a variety of choices for this threshold and pick the threshold to use as for your classifier, the one that strikes the best balance between error rates. I ask you to give me some specific error rates in the problem. For each choice of kappa, tell me a handful of different ways that you can characterize the accuracy of your model. With classification, there are multiple ways to define accuracy. So, for example, in the 2-class problem, like the Hall of Fame data, you're either in the Hall of Fame or not. We're going to model Hall of Fame as a function of our input variables. And we're going to classify y hat as whichever class has the highest posterior probability. So actually, we're going to do something a little more generic. We're going to say y hat equals Hall of Fame if the posterior probability of Hall of Fame, given the data, is bigger than or equal to some threshold. And it's not Hall of Fame otherwise. This is just another way of stating the Bayes classifier strategy. The default statement is that you'll predict to the class that has the highest posterior probability. We're going to tune this model by allowing for a specialized threshold. I'll predict a player is in the Hall of Fame if their posterior probability is bigger than or equal to kappa. So suppose we did that. We went through the 1,000 players in our data set, we built a model, and then we made predictions for each one of them. We will be correct some of the time, and we'll be incorrect some other times. And there's two ways that we can be correct. There's two ways we can be incorrect. So let's table this set of possibilities up. There is truth, that is for every player, whether they're in the Hall of Fame, the actual state. And there is our claim, or our prediction. So for each of these, we could have Hall of Fame or not Hall of Fame. So if I predict for a player Hall of Fame, and they are in the Hall of Fame, then I made a correct prediction. And similarly, if I predict they're not in the Hall of Fame, and they are indeed not in the Hall of Fame, I made a correct prediction. I make a mistake in one of these off-diagonal cells where I claim the player's in the Hall of Fame, but they're really not. Or I claim they're not in the Hall of Fame, but they really are. So when we come to characterizing a predictive model in terms of how accurate it is, the definition of accurate depends on what exactly we're doing. In the 2-class classification problem, there's multiple ways to define accuracy. There is sensitivity. which is the probability a Hall of Fame player is predicted to be in the Hall of Fame. We could call this a true positive rate. If the truth is positive, affirmative, yes, you're in the Hall of Fame, at what rate do we claim that? Correctly predict that yes, you are in the Hall of Fame. There is also specificity, which is the probability a not Hall of Fame player is predicted to not be in the Hall of Fame. And we could call this the true negative rate. The best classifier would be good on both of these, high sensitivity and high specificity. Unfortunately, we can't simultaneously maximize both of them. For example, in the Hall of Fame case, I could have perfect sensitivity if I predict that every player is in the Hall of Fame. If I say yes to every player, then I have 100% sensitivity, because for all the players who are in the Hall of Fame, I predicted them to be in the Hall of Fame. But in that case, I would have 0 specificity, because for all the people who are not in the Hall of Fame, I still predicted Hall of Fame. And you could go to the other extreme by always saying no. You'd have perfect specificity, but perfectly wrong sensitivity. Tuning a predictive model is about finding a good balance between the different error rates. There is a picture-based way to visualize the trade-off between sensitivity and specificity. It's called an ROC curve. And what it is just a plot of 1 minus specificity on the horizontal axis and sensitivity on the vertical axis. So suppose we took that kappa, the probability threshold we're going to use for classifying to the Hall of Fame, and we let it vary from 0 all the way up to 1 in 0.05 increments maybe. So I'm going to try kappa equals 0. I'm going to try kappa equal 0.05, 0.1, ... all the way up to 1. And for each choice of kappa, I would have a sensitivity and a specificity. If you're going to use kappa equal 0.3 as the threshold, you have a corresponding sensitivity and specificity. So for every one of the kappas that we consider, there will be a dot. And we will end up with a picture that most likely looks like that. So each point in your ROC curve is a single threshold choice, and we're going to tune the model to be optimal by finding at what point do I have the optimal trade-off between sensitivity and specificity. You would answer that by, I want specificity to be high, which means I want 1 minus specificity to be low, and I want sensitivity to be high. So I'm looking in this kind of region there, upper left. where in that region do I feel like I get the most bang for the buck, sort of? You'll get an example of doing that with your homework. So for your homework, I'm asking you to consider a variety of choices for kappa. Here's the choices that I'm requesting specifically. You don't have to go above 0.5. You never get posterior probabilities bigger than 0.5 with these data, just because it's so rare that players are in the Hall of Fame. So you're going to consider choices of kappa from 0 up to 0.5 in increments of 0.01. For each one of these choices, you'll have a sensitivity and a specificity. And then I have you make a couple of plots. You don't actually make a ROC curve, but you make one that's a lot like one. And then the task is, given an ROC curve or the pictures you're going to make in your homework, what's the best trade-off? What's the best LDA model for these data? This is new for us, cross-validation. I'll get to that Wednesday, I think. This is a trick for getting valid estimates of these error rates. I talked last time about the overfitting problem with classification or prediction. That is, the more complex the predictive model, the more accurate you will get necessarily on the training data. But you don't want to get arbitrarily accurate on just the training data, because then you'll be overly specialized to just the data set you had and won't do well when you try to make predictions to a more general population. There's two main strategies for avoiding overfitting. One of them is splitting the data into training and testing data. And I showed you in the slides from Friday a picture where as you increase the complexity, the training error got really, really low, arbitrarily low, but the testing error had a saddle in it. Getting more complex helped up to a point, beyond which it actually hurt to get more complex. One way to make that picture is by splitting your training data into some true training data and using the remaining data as a test set, a held out test set. You don't use the test set data in fitting the model. You only use it to assess its accuracy. Another way to do basically the same thing is a resampling trick. Kind of like Bootstrap, but not exactly. It's called cross-validation. So with cross-validation, you don't actually have to split the data into training and testing. You use all your training data for training, and you use a resampling technique or trick to make it as if you split into training and testing. So I'm asking you in the homework to do a particular type of cross-validation that, again, I'll show you more detail on Wednesday. Leave one out, cross-validation. And I want you to use cross-validation to estimate the error rates I'm requesting. Just to fill in the remaining blanks with these error rates, I have sensitivity and specificity. I just defined those on the whiteboard. There's also positive predictive value and negative predictive value. You can Google those or go to Wikipedia. They're comparable to sensitivity and specificity, but they're kind of like the Bayesian analogs of them. So positive predictive value is the probability in the Hall of Fame given that we predict Hall of Fame. Sensitivity is the probability we predict Hall of Fame, given that they're in the Hall of Fame. Positive predictive value is kind of the Bayes switched conditional order version of that. The probability they're in the Hall of Fame, given that we predict they're in the Hall of Fame. And negative predictive value is the probability they are not in the Hall of Fame, given that we predict they're not in the Hall of Fame. Computing PPV and NPV is just as easy as computing sensitivity and specificity. Once you've got your code written and have cross-validation running, those are real easy. All four of those are easy to compute. And then this fifth accuracy measure is something I've seen in research talks recently as a single number summary of accuracy. It's called balanced accuracy. And basically, it's a weighted average of sensitivity and specificity. The default choice would just be sensitivity plus specificity divided by 2. The reason it makes sense is because it's a one-number summary for accuracy, but it won't be tricked by the extremes I mentioned earlier, like you never predict Hall of Fame. If you never predict Hall of Fame, you have perfect specificity, but you have perfectly horrible sensitivity. Balanced accuracy would highlight that. It would point that out. Because if you had 100% specificity but 0% sensitivity, your balanced accuracy would only be 50%, which is not good. I'm specifically asking you to use a custom weighted average for the balanced accuracy. So instead of just sensitivity plus specificity divided by 2, I want you to upweight specificity. I've played with these data quite a bit, and the specificity is where most error happens. So in order to force us to pick a model that strikes a good balance between both sensitivity and specificity, I want you to use, for the balanced accuracy, what I have highlighted here. A weighted average of sensitivity and specificity. Sensitivity gets weight 1, specificity gets weight 3. So 1 week may be optimistic for this. We'll see. Keep me posted. Okay. So let's go back to the notes. We finished up this chapter 1 that was an overview of statistical learning. Now let's go, let's see what the next one is. How about we do model selection? So I'm going to download the chapter called Model Selection, and I'm also going to download the chapter called Resampling. We'll get to that one soon as well. That's where cross-validation is in resampling. So let's not do this chapter right now. Let's go ahead and go to the resampling chapter. When you download it, it's actually called CV Boot, as in cross-validation and Bootstrap. So let's go here. We're not going to spend we're not going to look at Bootstrap too much in the context of predictive modeling. It is applicable. Bootstrap is just, remember, a general technique for approximating sampling distributions. With predictive modeling, we might, for example, want an accuracy, like a balanced accuracy, and a standard deviation of that balanced accuracy. So don't just tell me that you're 92% accurate. Tell me how variable that estimate is. Is it 92% plus or minus 20 percentage points, in which case that 90% is not impressive at all? Or is it 90% plus or minus 0.1%, in which case it's very impressive? Bootstrap can always be used for getting variation estimates, like standard deviation estimates. We're going to focus, though, on cross-validation. Before I do that, let me just look real quickly at the introduction chapter, because it has something that is useful to get us started here. So let me get introduction real quick. Introduction is where I should have started instead of going to statistical learning. If you have time, I recommend you browse through the intro slides. It has some good motivational stuff, like why do we care about prediction? Show me some examples of prediction. You guys have heard of 538, Nate Silver. I know a lot of you heard of Nate Silver because he was here last year in this room. He came, visited Texas A&M, and met with a bunch of people on campus. He wanted to meet with the statistics group, and so we got to interview him. He's got this book, The Signal and the Noise, why so many predictions fail but some don't. And he does predictive modeling, statistical learning, supervised learning in the context of sports and politics. So he became famous because of his unnaturally accurate predictions of polls or of political races. And there's another interesting example in here, which was the Netflix challenge. Netflix challenge, which was 10 years ago. Maybe you heard about it. Netflix put up $1 million and said, here's a big training data set. Basically, it's data on users and what movies they have watched and the ratings they gave to those movies. Can you give us a predictive model, an F with a hat on top, that will improve on our prediction algorithm for predicting what movie you will like? Can you improve on our algorithm by X percent, 10% or something? And if you can, then you win $1 million. So that was a predictive modeling challenge. And now there's lots of these kinds of challenges out there. If you've heard of maybe of Kaggle.com, where there are open challenges posted by companies, by research groups, by the government, where they have huge data sets and they need somebody to put together a accurate predictive model. Let me just briefly go through some of these. They're interesting. Predicting things can look like a lot of different details. Is an email spam or not? Or, yeah, is an email spam or not? If you have text information on emails, then you can digitize the emails. And for example, if you could decide on keywords or common words or phrases, you could look for them, tabulate them, maybe compute relative frequencies of them, and use those as predictor variables. So I predict spam conditional on the predictor variables using pick a classification method, LDA or whatever. Or suppose you work for the post office and you're in charge of developing a computer algorithm for automated reading of handwritten notes, like addresses on an envelope. You might have a training data set that looks like this. Here's a bunch of zeros written by hundreds of thousands of people. And here's a bunch of ones written by hundreds of thousands of people. The training data would be these images and the correct classifications for each one of them, training data. Given that, you could represent each of these samples as a vector of pixel intensities, maybe. Digitize these images into an X matrix, n by p, some p predictor variables, which again could be pixel intensities. Classification and prediction is used in genetics quite a bit. This is called a heat map, where there might be tens of thousands of genetic entities like genes or proteins. And for each one of them, so imagine that each column in this image is a separate person, and each row is a separate gene. For each of n people, we get this genetic assay that is a number for a bunch of genes. Can you predict whether they have cancer or not? Or can you predict which of these 1, 2, 3, 4, 5 types of cancer they have? Y is cancer type. X, n by p, is the matrix of gene expression intensities. So all of these are interchangeable in terms of what you're doing. Y equals f of x. You're trying to build f hat and make predictions. All right, so I'm going to go back to CV boot. And let's look at this for a moment. On Friday, we talked about the different ways of assessing accuracy. There's the accuracy that you have with a model on your training data. And then there's a separate accuracy that you have with your model on data that were not used for training. You might say that there's like training error and there's generalizable error. Training error is how accurate can you be with your training data. Generalizable error is if we take your results, turn them into a predictive model, and take it out to the general population, like try to go make predictions of cancer in a medical clinic with new people. Those are different quantities. You can be really accurate with your training data and really not accurate with the test data. And vice, well, yeah, typically that's the direction it goes. So test error, here's the way the authors refer to it. Test error is the average error that you can expect when you use a model to predict the response on a new observation, one that was not used in training the model. So for example, with the Hall of Fame data, suppose we took our 1,000 players and randomly selected 667 of them to use for training, and the remaining 333 we're going to set aside as test individuals, and we're not going to touch them while we're building our model and tuning our model. We will only use that held out test set for estimating accuracies. Then those would be estimates of test error. That's the generalizable error. If you were to take your predictive model out into the real world and start making predictions out there, that's what test error tells you about. Training error is just the error that you get on the training data itself. These are often quite different from each other. And what we're trying to avoid is overfitting, where the training error is deceptively low. The training error is low, but the generalizable error is high. So this is a picture like the one we saw on Friday that illustrates the overfitting problem, potential problem. For more and more complex models, which might be like curvier models or functions or curvier surfaces, you will tend to get lower and lower training error. But beyond a certain point, you'll actually hurt the test error. Think about model selection going between very simple to very complex models as you're adding in additional pieces of information to your model. You're making it more complex by, for example, adding additional covariates, predictor variables. So adding more covariates will always reduce the error in your model on the data you're working with. But thinking in a general way, generalizable error, some of the variables that you add to the model may just be noisy variables. They may not actually be related to the quantity you're trying to predict. In which case, adding those is only going to hurt the accuracy of the model because you're adding noise to your model. So our goal is, when we're building a model and tuning it, to use an estimate of the test accuracy as our guide, not training accuracy. And again, the two ways that we can do that generally is splitting the data into training and testing. That's one option always. Or using a trick called cross-validation. The split into training and testing is not always ideal, especially when you don't have a lot of training samples to begin with. So if you have an expensive assay and you have just a dozen or a few dozen samples, or maybe you have like a really big number of predictor variables, P is really big, but N is relatively really small, then it's not appealing to kind of artificially hold out some of your training samples. You would prefer to be able to use all your training samples. So especially in cases like that, people like cross-validation as a technique for using all the training data for model building and tuning. So the authors say the best solution is the train-test split. In particular, a large test set. The reason that's best is because it's most easily justified as being unbiased and giving you reliable estimates in the general population. Another option that we won't go into much today or in this class is to work with training error, so not a test set, just use training error, but then try to do some post hoc mathematical adjustment to the training error to adjust it to be generalizable. Things like AIC and BIC, if you've seen those in regression output, Aki-Iki information criterion and the Bayesian information criterion, that's what they're there for. They're a measure of model accuracy that are specifically designed to avoid the overfitting problem. So we're going to talk about cross-validation, which is a method of holding out a subset of the training observations. It's not a designated test set, but it's an iterative procedure where, for example, we might, well, I'll leave it for next time, but we're going to hold out a subset of the data, fit the model with the remaining set, and then assess it with the held out set, just like a train test split. But then you iterate and do that again with a different held out subset. train it on what's currently training, evaluate it on the held out. Repeat, repeat, repeat until every individual has been used as a test individual once. Then essentially we average over those iterations, and that's cross-validation. So I'll have to pick back up with that on Friday, but if you want to read ahead in the homework, I ask you to do cross-validation, specifically leave one out cross-validation. So beginning on slide 9 is a general description of cross-validation in terms of k-fold cross-validation. Leave one out cross-validation is like n-fold cross-validation. So if you understand k-fold, you can understand the leave one out. But we'll pick up back here on Wednesday. Okay. Thank you.